Hi, my name is Tom Heffel, and this channel is all about helping students learn chemistry. In this video, we're determining the rate order quantitatively. Okay. Now, the reason why we have to do it quantitatively is because these numbers are a little bit more challenging than what we had yesterday's video. And in yesterday's video, we watched and learned how to figure out the rate order qualitatively by using this chart over here, where if the reactant doubles and certain things happens to the reaction rate, where we could determine if it's zero order, first order, or second order kinetics. Okay. Well, the numbers that we're using today are a little bit more challenging, where we can't do that because we can see that the reactant isn't doubling. So we can't use this chart, but there is another way. Okay. And that's figuring this stuff out quantitatively. Okay. So let's get started with this problem. Okay. So in this problem, we have a reaction where A plus 3B is going to yield 2C and D. Now, we can write kind of the rate law. Basically, it's template, and the rate is going to be equal to the rate constant K times each of the reactants, and the reactants here are going to be reactant A and reactant B to a certain power, okay? And the X and Y are the exponents, and that's what we call the rate order. So X is the rate order on A, and Y is the rate order on B, and that's what we're trying to figure out. Just like we did that yesterday, we did that qualitatively, but since these numbers are a little bit more challenging, we're going to have to do it quantitatively. So what we need to do is find two experiments where one thing stays constant, like the B is constant here, and the A is changing, and the reaction rate changes. So we can actually figure out, well, this concentration change on A, what is going to be the reaction rate will determine kind of like what X is equal to. It's probably going to be 0, 1, or 2. And the same thing for B. Okay, we want to fluctuate B, but keep A constant. In experiments 1 and 3, A stays constant, but B fluctuates, so the reaction rate fluctuates as well, and that's how we're going to eventually figure out what Y is equal to. And we're going to do all of that quantitatively. So let's go ahead and get started, and let's see if we can figure out what X is equal to. Now, to figure out what X is equal to, we're going to compare experiments 1 and 2 because B stays constant, and we can focus in on this change and this change to figure out what X is equal to. So we're going to be comparing experiments 2 and 1. So I'm going to put experiment 2 on the top and experiment 1 on the bottom. Okay, so what I'm going to do is I'm going to just write everything for line 2 for experiment 2 with the rate law. So the rate is equal to 0.522, and that's equal to K times the concentration of A and B for experiment number 2. So that's going to be 0.394 to the X and 0.507 to the Y. And I'm going to do the same thing for experiment number 1. Now, in experiment number 1, the rate is 0.191, and that's equal to K times A and B, and A and B for experiment number 1 is 0.238 to the X and 0.507 to the Y here, okay? And when we do all this, okay, what we're going to do is we're going to get some things that cancel out. Now, it's really obvious to see that the K's cancel out. That's really easy. But the other thing that cancels out is really important. This 0.507Y cancels out because we kept those things constant, okay, and that was by design. So what we're going to do is we're going to take 0.522 and divide it by 0.191. And when we do that, we get this number of 2.73. And that's going to be equal to these two numbers divided by each other, which is going to be 1.655, but it's to the X power, okay? And since it's to the X power, and that's what we're trying to figure out, we're going to use our log rules, okay? And I'm going to use natural logs, but you could use natural logs or regular logs, okay? And I'm going to take the natural log on both sides. And when I do that, I get natural log of 2.73, and that's going to be equal to x natural log of 1.655. So when we take the natural log on both sides, that's what brings this out of an exponent into becoming a regular number, okay? And that's just one of the rules that we have in math on using anything that's a log, either natural logs or regular logs, okay? And then from here, it gets really easy to solve for x, okay? I'm just going to divide by natural log of 1.655 on both sides, and I'm going to figure out, so I'm going to take in my calculator, I'm going to hit natural log 2.73 divided by natural log of 1.655, and I get this number of 1.99, okay? Now, rate orders tend to be whole numbers, 0, 1, or 2, so we're going to say, hey, this is close enough to being a rate order of 2. So we just figured out the rate order on A, or which is the exponent x, and x is going to be equal to 2, okay? And that's how we figured out the rate order quantitatively. Now, we still have another rate order to figure out. We want to figure out what y is, okay? Now, to figure out what y is, we're going to pick two experiments where A stays constant, but B changes, okay? So that would be experiment 1 and 3, where A stays the same, okay, but B fluctuates, and obviously the rate is going to fluctuate, and because of that, we're going to be able to figure out what y is equal to. So we're going to compare experiments 3 and 1. I'm going to put experiment 3 on the top and experiment 1 on the bottom. So experiment 3 has a rate of 0.230, and that's equal to K times the concentrations of 0.238 and 0.611. 0.238 to the x, and then 0.611 to the y. And then we're going to put experiment 1 on the bottom. Okay, now if you remember, this was experiment 1, so I'm just going to transpose this again. 0.191 is equal to K times 0.238 to the x, and 0.507 to the y. Okay, and as you can see here, the k's are going to cancel out, but also the 0.238 to the x is going to cancel out. So I'm going to divide these two numbers, 0.230 divided by 0.191, and when I get that, I get 1.204, and that's going to equal to these two numbers divided by each other to the y, though. So, and when I do that, that equals 1.205 to the y, and then I'm going to do my natural log stuff. So the natural log of 1.204 is equal to y natural log 1.205, and to solve for y, I'm just going to divide by natural log 1.205 on both sides. And as you can see, these are pretty much the same number, but if you put them into your calculator, you're going to find out that y is equal to 0.996, which is approximately 1 when we talk about whole numbers. And obviously, whenever you have the numerator and denominator that are the same value, that's going to equal to 1 when you divide the same value by the same value. So y is equal to 1. Okay, so y is equal to 1. So our rate law becomes k times a to the second power and b to the first power. And that's how we write the rate law and figuring out the rate orders quantitatively. If you found this content helpful, please give it a like and subscribe. When you add that comment, it pushes this chemistry stuff out to other people that are interested in learning how to become a pro at determining rate orders quantitatively.